Relations for a homogeneous phase. In the preceding section, we established the mean to calculate differences in enthalpy and entropy between different phases in terms of properties that are readily measured, such as the Clapeyron equation. FF on VFG TVF G also can be used for HFG or TVFG. We will develop expression for calculating differences in these properties within a single homogeneous phase. Assuming a simple compressible substance, in order to develop such expression, it is first necessary to present a mathematical relation that will prove useful in this procedure. Consider a variable that is continuous function of x and y, a variable dz on z on rho x It is convenient to write this function in the form dz m dx and on x constant. Partial derivation of z with respect to x, the variable y will be held constant, and partial differential of z within y with the constant x. The physical significance of partial derivative as they related to the properties of a pure substance can be explained by referring to the figure provided here, which shows a PVT surface of the superheated vapor region of a pure substance. For example, T, a specific temperature, a specific volume, and pressure are shown in this picture. It shows constant temperature, constant pressure, and constant specific volume planes that intersect at point P on the surface. Thus, the partial derivation P rho P on rho V is the slope of curve ABC, A, B, C. ABC rho P on rho V at T constant. As we see, we have this on the temperature plate. Is the slope of the line DE represents the tangent to the curve ABC at point B. This line DC is the DE. Represents the tangent to curve ABC at point B. To curve ABC at point B. A similar interpretation can be made of the partial derivation of round P on round T at P constant and round V on round T at P constant. If we wish to evaluate the partial derivation along a constant temperature line, the rule for the ordinary derivation can be applied, as we can write for a constant temperature process round P on round V, T constant, dVt, and the integration can be performed as usual. This point will be demonstrated later in a number of examples. Let us return the consideration of the relation dz equals to m dx m dy for z, x and y. If x and y and z are point function, that is, quantities that depend only on the state and are independent of path. For example, energy dE the differential are exact differential. If this is the case, the following important relation holds: round m on round y x, round n on round x, the proof of this so we have this on m or for Z, X, Y a mathematical relation for a homogeneous phase. The Maxwell relation is the next section.